Hello everyone, welcome back to another video. Today we're going to be looking at the questions from the Doppler Effect from the KZN June 2023 paper. As always, if you'd like to give the questions a go, please pause the video. I'm going to go through the answers in 3, 2, 1. Question 1.7. The hooter of a car emits sound waves of constant frequency as the car moves away from a stationary listener. Let's sketch this out. Stationary listener. There is a car, don't mind drawing, and it is going, let's say it's moving away. Which of the following properties of the sound waves heard by the listener will not change? Okay. So we have to understand that this car is emitting a sound wave, and it's emitting a sound wave in all directions. So it could be emitting it this way, and it could be emitting this way. Now, as the car moves, what's actually going to happen is that it is going to compress the sound waves that's in front of it. So the waves that are in front of it are actually going to appear closer, like this. And the waves behind it are sort of going to be dragged. So in other words, they're going to be maybe stretched a bit, like this. So that's why we say that there's an apparent change in the frequency. Because remember what happens here. Here we can say that the wavelength has decreased. And since the wavelength decreases, the frequency increases because the speed of sound is constant. Remember, V equals F times lambda, right? If the car is moving, it's going to be changing the wavelengths. And if the wavelength is either increasing or decreasing, that's also going to have an effect on the frequency since the speed is constant. So the answer is A. Okay? Let's move on. Question 6.1. The siren of a car emits sound waves of frequency 650 Hertz. So let's just write that down. The frequency of the source is 650 Hertz. The car is driven at a constant speed along a horizontal road. A detector placed on the side of the road registers changes in the pressure of the air caused by the sound waves. Assume that the speed of sound in air is 340 meters per second. So V equals 340 meters per second. Is the car moving towards or away from the detector? Motivate your answer by means of a calculation. Now, it's only possible to do a calculation from the graph, right? So we need to interpret what's happening here in this graph. Now, recall from grade 10, this looks like a transverse wave. It looks like a transverse wave. And in transverse waves, remember, we did some calculations, and one of those calculations was frequency. Now, if we calculate the frequency, and then we compare it to the frequency of the source, we'll then be able to make a conclusion or make a statement of whether the car is moving away from or towards the detector. Now, in case you may have forgotten, you can calculate the frequency of a wave, a transverse wave like the one that we have here, in one of two ways. So question 6.1.2, you can calculate the frequency by saying 1 over t, where t is our period. And remember, period is the time taken for one wave. Now, this wasn't given to us, so I wouldn't recommend using this formula, though you could work it out. Another formula to calculate frequency is frequency is equal to the number of waves divided by time. So in this case, if you look at this diagram, how many waves are appearing here? So from here to here, that's one wave. If we break it up, this is half a wave, that's half a wave. Now if we have to extend this to this point here, that's actually a quarter of a wave. So half plus a quarter is 1.25 waves. And the time taken for the wave is shown for us, or shown to us. So the number of waves that's shown in this diagram is 1,25 divided by the time taken is 17,36, be careful now, times 10 to the negative 4. If you put that in your calculator, you get an answer of 720,05 hertz. Now remember, this is the frequency of the listener, right? This is the frequency of the listener. Now we know that the frequency of the listener is greater than the frequency of the source. So the frequency of the listener was 720, the frequency of the source was 650. And whenever we have a scenario where the frequency of the listener is greater than the frequency of the source, it means that the objects are approaching one another. Okay. Next question, 6.1.3. Calculate the speed of the car. So 6.1.3. We always start off by writing your formula. FL is equal to V plus minus VL divided by V plus minus Vs multiplied by Fs. Always write the formula as is given to you. Now we need to decide whether we're going to use plus or minus in the numerator and denominator. So always remember that in this case, they are approaching one another. And if they are approaching, you're going to have a plus on the top and a minus at the bottom. I generally say you have a big top and a small bottom. So in this case, you're going to have V plus VL divided by V minus Vs times Fs. Now all we need to do is substitute. We know FL, we worked it out. So 720.05 equals 340 was given to us, plus VL, the listener is stationary, so 0, divided by 340 minus Vs, that's what we want, times Fs was given to us 650. And then you solve, you're going to get Vs is equal to 33.06 meters per second. Okay. Next question, state two applications of the Doppler effect in medicine. So in medicine, you could say, again, this is just theory. So you could say it's used to detect blocked arteries. It's used to detect heartbeat for babies. There are others, but just learn the simple ones. Question 6.2. The spectral lines observed for a distant star show that the star is moving away from Earth. Explain by referring to frequency how one can deduce that the star is moving away from Earth. Okay, so let's understand what's happening here. When a star, so let's go with our colors first, right? So the colors in the spectrum are R, O, Y, G, B, I, V. And this is in order. So if we go this way, that is increasing frequency. Okay? So if a star is moving away, there's two colors that we talk about, or movement of stars. We talk about blue and we talk about red. If a star is moving away, we say that the star is red shifted. And why do we say that it is red shifted? Because red has a high wavelength, right? So you can imagine that if there is an object, and here's Earth, that object is emitting radiation. It could be ultraviolet, it could be whatever it is, right? And it's emitting it just like sound, emitting it in all directions. Now, if it's moving away from us, then it's going to compress the radiation that's in front of it, but it's going to drag the ones that are behind it. So the wavelength for the ones that are behind it are going to increase. And an increase in the wavelength means it's going to appear red. But remember, they want us to talk about frequency. So how will we say, how will we answer this in terms of frequency? We will say that it's going to, so this would be the answer. The star would appear red shifted, right? And the frequency of the lines, I think it was spectral lines, would decrease. Because remember, red has a high wavelength, but it's going to have a low frequency. Okay? And that's it for this paper. If you found it useful, please consider leaving a like, sharing, subscribing. If there's something specific you'd like me to do, please let me know down in the comment section below. Until next time, bye-bye.